Good afternoon, everybody. Good afternoon to the warm people of Sudan. I'm very happy and honored to be here again today. Now, for the people who have seen me, interacted with me for the past 3 days, they will notice that I'm a preacher. Yes, I preach the gospel of technologies that are old enough to be in Africa, but they are not in Africa yet. I just finished a 3-day session with IPv6. IPv6 is 22 years old, and there's next to nothing in Africa. Today, I'm going to give you a crash course in a technology that turns 10 years old next year, with the hope that I'm going to sow a seed into your heart and we'll start growing this technology on this continent. Now, there are many buzzwords around in network computing, software-defined networks, network functions virtualization, VXLAN, and so many things. This session, I'm trying to clear the smoke very quickly because we don't have that much time on software-defined networks using OpenFlow. And part of this session, I intended to show you a demo of what I've done, a little work on SDN, but because of time, we can't do that here now. But after the session, please feel free to come and see me, and I will talk about it. It's not working. Happy. Okay. So this is the agenda. Let's just quickly go through this. So, like I said earlier on, as network engineers, we should embrace every technology that comes into the niche that we operate. Okay? Okay. Into the niche of every technology that operates in our niche, we should embrace it. Not that because we just know IPv4 or we know how to configure OSPF on Cisco routers or something. Embrace every technology. Now, this technology, software-defined networks, is a complete paradigm shift. It's a different way of networking entirely. Okay? Just like IPv6 is a different way of IP addressing. So, like I said earlier on, we'll be looking at the fundamental concepts behind software-defined networks. So, legacy network architectures. What do you know? I mean, what we know about today? We have this kind of devices. Sorry. Where we have our control plane, the data plane, the manager's plane, all incorporated into a single device. That's not funny. Okay, all incorporated into a single device, which inherently makes these devices very, very complicated, believe it or not. Okay? And also again, moving forward with the legacy architecture we know, it employs a sort of distributed computing model where each node on the network has its own control plane, its own forwarding plane, basically its own control plane. Where, for example, like OSPF, you run your SPF on a single router, it sends updates to other routers, and they have to do the same thing. So it's a distributed computing model. Okay? So two things. Everything incorporated into one device, and then you have a distributed computing model. Now, what are the challenges that we face within the current legacy network architectures we have? Scalability, that's why we have multi-area OSPF already. Technically, security issues also plague SDNs, but we have it here in legacy network architectures. Then we have limitations by vendor locked-in. So, well, thank goodness, Cisco eventually revealed or opened up EIGRP as an RFC last year. Well, typically, you have different vendors implementing different technologies in their own way, and you're locked to that specific vendor if you have their device on your own network. Okay? It's not open, it's closed. Network management. So if you want to configure like 20 routers or whatever, even with your Ansible or whatever, it's still error prone. A lot of human error can still come into it. Okay? And then finally, I said innate complexities, which I will shed more light on as we move on. So, what is software-defined networks? Like I said earlier, it's a paradigm shift. It's a completely different way of networking. It's a different architecture. And what is this architecture like? You basically decouple the control plane from a network device and put it on a centralized computer or server. And then you have just the forwarding planes on your network. With this style or this architecture, you have a centralized control plane. Okay? And next to dumb forwarding planes on your network. As compared to the distributed model you have, or we have in these legacy architectures we run mostly on our networks today. So, this is the SDN architecture. Basically, you have the control layer here, which is the network controller, the one in the middle here. That is the one that is centralized. You have multiple forwarding planes all over your network, which don't have any compute or minimal compute. And then you have the upper layer on the controller, where you have different not-bound APIs that you can use to program your network or program your data forwarding planes on your network. The controller also gives you, presents a southbound API, which is the most popular one now, which I'm going to use today, is OpenFlow. You can use other protocols. You can even use BGP. There's another one called OpenFlow Switch database. They are different. But OpenFlow is the most common. And to explore that illustration again, this is the SDN architecture, where you have, I've put a line here for you to show the demarcation. This is the control plane, and this is the data plane, which is these three switches here are data planes. You have the network controller, which gives you OpenFlow as a southbound API, and you have a network operating system which presents a northbound API. In most cases, it's a REST. Most controllers implement a REST API, but this is not a very standard. This is not a defined standard yet. So we have different northbound APIs, but OpenFlow itself is the standard already for the southbound API. And I want you to take note of these two arrows, the packet out and packet in. This is with respect to the controller. So if you look at Wireshark captures between an OpenFlow switch and the controller, you will see a packet in, packet out packets, and they all have different functions, which we'll look at briefly today. Now, these are the different. Like I said, my job is to preach technologies that are old enough to be here, but are not here yet. All these big guys have already adopted OpenFlow or software-defined networks in one way or the other. Okay? Juniper, Cisco, Oracle, BT, BT is an ISP, big ISP there in the UK, Orange, all of them. Now, pictorially, look at us. SDN. Though Asia too is not doing too good, so we have North America and the rest of the world. So I am trying to sensitize us with this technology. Now, what is the advantage of the SDN approach? Like I said earlier on, that's central. The first item there, centralized management. You have one point where you manage your network. You don't have to telnet or SSH to different devices to manage your devices, your network. And that also reduces your error in configurations. It's less error prone. Loop avoidance at layer 2. So basically, if you don't have layer 3 switches, you are at the mercy of spanning tree. So if you see networking 101, you build your network with access, distribution, and core. STP will block links all over the place, and you might be using just one part of your network, which reduces your bisectional bandwidth. But with SDN, and no controllers, Floodlight for example, or Open Daylight, they will do shortest path forwarding at layer 2. There's a new technology now, I think it's Trails. You have to use routing bridges to do that at layer 2. And like I said, this adds more complexity to the whole picture. All right? So network virtualization, you can do network sharing, infrastructure sharing easily with an SDN controller or SDN implementation. And there's also a cost benefit to it. Like I said, you don't have your forwarding planes are somewhat dumb switches now. They have minimal compute. They are just bare metal switches. They are quite affordable. They're not a high-end switch with all the new features, all the bells and whistles blowing on it. No. Okay? And then finally, this is says dedicated channel for controlled traffic. Although research has shown that to an extent, SDN generates a lot more controlled traffic than you have with your legacy network. And then challenges facing SDN, latency, number one. You will see later on that for every new packet that comes to a switch, and the switch doesn't know about it, it has to forward it to the controller, and the controller has to take a decision. That will introduce some latency. Okay, controller switch latency also, it's there, okay, because the control plane is on another machine. It's not within the same box. The TCAM tables, which your flow tables in OpenFlow switches use, are power hungry and relatively expensive, more expensive than what you use in your MAC address tables. Scalability, how many switches can a single controller handle? You have to look at that. Redundancy, well, with OpenFlow version 3, that has been corrected, where you can have multiple controllers connecting to the same switch, because once the controller dies, what happens to the switch? It has no brain anymore, okay? And then security, because a controller is usually running on a machine, on a server, for example, so you can do a denial of service attack on a controller, and it might not be able to do anything to your switches anymore on your network. You're stuck. And then the level of awareness, which is what I'm here, and the skill set. Fact, most of us network engineers don't like programming. Am I right? Yes, we don't like it. Well, we've been forced to like it, because you need to program if you're going to do SDN. Okay? All that programming you do, configure terminal on your Cisco devices, piece of cake. Okay? So the learning curve is a bit steep. Okay? So what are controllers? Network control, OpenFlow controllers or SDN controllers provide a central place for management. The controller has the full view of the network. That includes the switches, the links, and the end nodes, servers, clients, all over the place. Okay? And like I showed in the diagram earlier on, it gives you, it presents you a northbound API for you to program your switches, and a southbound API, which is OpenFlow, which actually manipulates the flow tables on OpenFlow switches. So basically, like the demo I was going to show you, because you actually exchange different packets between OpenFlow controllers and OpenFlow switches. The one I used in my application had to do with the network traffic. It's for traffic engineering. OpenFlow presents port statistics, okay, between a switch, traffic flowing to a switch, to a controller. You can use this information to, for your own use. Program something, usually it has to do with QoS or traffic engineering, okay? So, how does, I just said it now, the controller has the entire view of the network. How does it achieve this? It's not magic. It's LLDP, which we all know. We all know what LLDP is, right? Link, layer, discovery, protocol. Yep. So each OpenFlow compliant switch uses LDP, which is sent to the controller, and the controller uses that to build the network of switches. It is when hosts start communicating that the controller starts to build, the view of nodes on the network also. Okay? So these are different controllers on the market now. It's a bit small, I know, I'm sorry. The one I used was Ryu because it's written in Python, which is very simple, and I could find my way around it. A very good one, which is a lot of big players are working on it right now, is Open Daylight. Okay? That is very big, but I got lost in it. So I'm using Ryu. And you can see this OpenStack. Are we all familiar with OpenStack? OpenStack integration with Ryu and to some extent with OpenStack, with Open Daylight now, okay? So you can see you can integrate SDN into your cloud environments also. Now they're saying OpenFlow. Now OpenFlow, like I said, is the standard or the most popular southbound API which SDNs use. So it's basically if a controller wants to send instruction set to the forwarding planes, or the control plane wants to send instruction set to the forwarding planes, it uses the OpenFlow protocol. And it runs by default on TCP port 655 actually. 63 is now legacy. 6653 is the IANA assigned port now. Okay? So we have different types of OpenFlow OpenFlow messages. We have the controller to switch, which is usually sent by the controller to the switch, and that will be a packet out message, as you saw in the diagram. And then you have the asynchronous messages, which could be sent either way without any event triggered. And then we have symmetric also, that is sent by either a switch or a controller. So this is also very small. This is a controller to switch message here, which is a feature request. The controller is asking the switch for a request, for its features, requesting for its features. And that's how the controller builds the network with the capabilities of the different devices on the network. This is also, this is actually supposed to be a controller to switch, I'm sorry. It's also a packet out message. And this is an asynchronous message. This particular packet is a packet in, and it's sent by a switch to the controller. And why is this? This is because the first packet arrived at the switch did not know what to do with it, and it sent the entire packet. You can see why I said some of the control traffic in SDN is a bit much more. This is the entire packet of the first flow sent to the controller. Okay, so you also have some unsolicited messages. So hello, just like you have in routing protocols, I want to know if my controller is still there or not. Okay. OpenFlow switches. Okay, so you have different types. Actually, you have the pure OpenFlow switches. You have the hybrid switches, which run both OpenFlow and run the legacy way. And basically, they perform the function of rewriting headers of a packet that arrives at the switch. Or if it doesn't know what to do with it, send it to the controller. Now, in an OpenFlow switch, as you've seen on the graphic later on, you have both a MAC address table and a flow table. Okay? Because in software-defined networks, we forward traffic based on flows, not destination-based forwarding. Okay? So you have different OpenFlow compliant switches. I know HP for sure. So this is the flow paradigm. Like I said, this, for example, when you have a port and a destination MAC, that is switching. Okay, that's simple switching. You have a port, you have a destination MAC also here, you have a firewall. Now, with flow switching, you can use any of the headers, any of the fields in the header for taking any action on the packet. Okay. The most basic one is to be the import. If it comes in through this port and is going to this destination, do that with it. Okay? It's not just destination-based forwarding. This is the flow switching paradigm. Now, a bit small, but this is the logic behind it. So where you have a packet comes in, the switch passes the headers. If there's any instruction in the flow table, it acts on it, it takes the actions on it. If there's not, it forwards it to the controller. So topology discovery, I will quickly do this quickly. Have a little time. So this is a simple SDN network where we have the switch here has a MAC address table and a flow table which is empty. Now A wants to communicate with B. A sends an ARP request. It gets to the switch. The switch does not know where B is. Okay, and ideally, what happens in our legacy architecture? Flood all over the place. Okay, so what does the switch do? Well, the switch knows now that A is connected to this port. That goes into the MAC address table. What does the switch do? The switch sends a packet in to the controller with that ARP packet. Okay? And what does the controller do? The controller sends the packet out and tells the switch to flood. See where the latency comes into play? Although it's very fast. Okay? But now the controller knows where A is. See how the controller builds up nodes? And then he floods. Switch B, again, does not know what to do with that. because B hasn't communicated yet. What does it do also? It sends a packet into the controller. What does the controller tell you? The controller tells him to flood. Okay? And when he does that, B receives the ARP request. And when B replies, what does it do again? Asks the controller. But this time around, because the controller knows where A and B is, is going to, there's a particular OpenFlow message called the flow modification. The controller uses that to program the flow table of the device. Now, here you have the flow table, which a bit in small print, but it has an action, an input source and destination, and an action. Okay, it's different entirely from a MAC address table. So you use different fields in your header to make a decision of forwarding. And this basically unifies the functions of a device. So your switch, your dumb switch in your network, based on what you do, can be a firewall, it can be a router, it can be a normal switch, if you're using a flow approach. Okay? Because you have access to all the headers, fields in the header. So also, I'll quickly go through this. In response, because they don't know what to do, they're going to ask the controller again, but the controller has to program. Remember, the flow is only in one direction. You have to program the return path also. Okay, and this is where the controller programs the return path. Now, like I said, I was going to show a demo, but if you please feel free to see me after this session. You'll find me where there's food, or tomorrow I'll be here all day, okay, doing nothing. So you can come and see me. So like I said, in my own demo, I use the Ryu OpenFlow Controller because it's written in Python, and I was able to find my way around easily. I said it earlier on, it's a bit of a steep learning curve, but with a lot of interest, you will find your way. I put a link also to the files, the code, because actually I modified there's a switch class and a traffic monitor class. If you're interested, if you want to see it, I put a link to where you can download the files. Now, basically what the application does, because if I had shown the demo, it would have shown you this kind of output. Every flow that goes on the network, it gets the throughput of that flow and the packet loss. Okay, now this I was going to implement on a small enterprise network where, like I said, in OpenFlow or in software-defined networks, you have shortest path forwarding at layer 2. Okay, so let's say on my access distribution and core, all implemented with multiple links all over the place, like cobwebs. If I see that this particular link or this particular flow is hogging all the bandwidth on this link, I can redirect it to less utilized links on the same infrastructure automatically. Okay. All right. So this is the general idea behind this particular application, which was written on the controller, and the switches don't have any form of control logic in them. Okay. All you have to do is once the flow gets into them, they inform the controller, and I get all the necessary parameters to know. Periodically to query that switch to know the throughput of that particular flow, and if it's violating or it's overutilizing that link, hogging that link. Okay, so that was the sample. That was the demo topology, which I was going to run different flows all over the place. So, like I said, you can simulate it for that. Thank you very much. Sorry, I was a bit quick. Any questions? Yes, please.
Thank you for your active topic, really characteristic so much. But I want to know what is the maintenance problem you usually approach? You talk about the advantages and also you talk about the challenges, but you don't put the light on the maintenance problem. If some router is crashed, if the networking to be developed or something like this. The advantage, the maintenance.
The maintenance.
Good and the advantages or the challenges. Thank you so much.
Okay. Well, based on my experience, you usually don't have any challenges at the switch end, but at the controller end, yes, you might have encounter several challenges because at least I worked with open source controllers, so you might experience something like an application closing unexpectedly, just like that, without you, without any warning whatsoever, or consistent memory use on the server by controller. So usually, like I asked the question earlier on, we don't like programming. We don't like programming. If you look at the beginning of this slide, we have two, myself and another guy. He's a system admin in Afrinic. He actually rewrote my very dirty code for this particular application. So probably, I mean, to the best of my knowledge, you have issues at the controller end, not at the switch end. And it still boils down to that steep learning curve. Okay? Are you okay? Thank you. Any other question, please?
I would like to thank you on your very presentation and the guidance of this technology. I would like to ask if there is any kind of simulator application or something to get familiar with the...
Yes. Actually, one mistake I made, because the demo I have is actually I implemented it on the VirtualBox. I could have created an image of that and give you guys a link to download it and run your, I'll do that, but I don't know how to get your contacts. But Mininet is a very popular tool for simulating or emulating software-defined networks, particularly in research. I used to work in a university, and that's what I used. Most of the SDN controllers are open source. Ryu is, I can show you the documentation pages, well documented. It's all over the place. Open Daylight even, it's open source, despite the fact that Cisco, big giants are working on it. It's all open source. So the tools are there for you to play with. If you have the bandwidth to download, I'll give it to you. All right, thank you. I should get up a bit.